Okay. So to continue here with this example that we did last time again, we have the ultimate load, which means factor load. And the question was about the amount of reinforcing that you need to use there. So what we have done here, we were able to find out the ultimate stress or contact pressure between the footing and between the soil. And this ultimate pressure here, we're going to use it as if it is like loading to this footing. Critical section for the moment is going to be right at the face of the column in both directions, this way and that way. And because this footing here is a square and the column is a square, this section is going to be exactly the same as this section. It does the same thing. Because this X is going to be the same in both directions. And the pressure also is going to be the same throughout the entire footing, which means in both directions. With that, after I find out the value of X, I was able to find out the moment, since I'm going to have here big point load pushing this piece up, this piece of the footing up. So the moment arm is going to be equal to X over 2, and the force is going to be equal to the pressure multiplied by this area here, the shaded area. Exactly what we have in this equation. Once you find out the moment, now you can check the amount of reinforcing provided and just find out Vmax. So what I have shown here is a way of estimating the amount of reinforcing. And in this case here, I estimated that D minus A over 2 to be in roughly 90% of the depth. Someone else can have done it 85%, or maybe 95%. Doesn't matter. This is just the first estimate. And after you come up with the amount of reinforcing, you need to back check and find out Vman. And of course, you need here to find out the phi factor that I didn't show. Because now you become here expert in this issue here. You know what to do. You find out the strain or C over D, and then after that, you find out the phi factor. So I'm going to put here a note, phi factor needs to be determined. I didn't show it here, but I'm not expecting that you're going to be solving an example or homework or exam, and then you're not going to be finding out the phi factor value. You need to work on it. To find out the shear, we're going to be going at D distance away from face of support, like what we have done in the beam shear design. This depth is about 26 inches, so that this X distance is going to be equal to the total cantilever length, 3 1/4 is the total cantilever length, subtracting this depth, but in terms of feet. So I'm going to end up with this X to be like just a foot. Now we can figure out the amount of force which is pushing this piece up. So I'm going to say, let's say this is going to be coming from the bottom, pushing this up. Let's say at the centroid here, and this is going to be equal to Q ultimate multiplied by B multiplied by X. So this area here is going to be the area over which the pressure is pushing this up at the face of the critical section, the side of the critical section. I find out that here the ultimate shear is going to be factored. Why factored? Because the stress also is factored to be 86 kips. There is no ties here to take the shear, so I'm going to be using only phi VC. Here is the phi factor, cross-section area exposed to shear, which is the depth multiplied by the width of the footing. It's going to be this section here. Just imagine if you cut this section here with a knife. You cut it this way. The area that you cut through is going to be equal to the width, 8.5 feet. Of course, you multiply by 12 to put it in inches. Multiply by the depth D, the 26 inches. So here's the width multiplied by the depth times 2 square root of A prime C divided by 1,000 to put in kips. Divided by the phi factor of 0.75, which is the same for all shear cases. And with that, you have a capacity of, let's say, roughly 218 kips. Now, compared to the demand, this footing is good. So now what I have done here, I have checked the flexure, which means the amount of reinforcing that I put in here. This is going to be for the reinforcement. And also I checked what I called here one-way shear. Today also I'm going to be showing you the two-way shear, which is a punching check or punching shear. We're going to be going through it today. Any questions? All right. So what happened here in this example, I have service load of 600 kips and the service moment is 720 kip foot. And this is going to be a footing of a moment frame count. So you have concentrated moment 720, and then you have service vertical load 600 kips. Have you guys seen this before? An example similar to that kind of numbers?
Yes.
Yeah, so what is the difference? What's happening here in this case?
A large moment.
Yeah, but what's important is I'm not trying to find out here the pressure below the footing to do the size of the footing. I'm trying here to do the reinforcement. So it's really about the reinforcement in both directions. It says here longitudinal, transverse direction. Longitudinal direction means in this way. Transverse is going to be the reinforcing in this direction. So in a case like this, it is true that I use the same values here when I was trying to find out the stress distribution and be sure it's going to be within the allowable. But the problem that I'm facing here now is to find out the reinforcing. And in this case here, I need to find out the ultimate loads. When you see here vertical service load 600 kips and service moment 720 kip foot, now we are going to be wondering which load factors that I need to use. How much is a dead load? How much is a live load? I don't know. I don't have it in split. So I'm going to be using an average value, which is 1.4. So as it says here, after I find out the service stresses, which we have done this step before, you guys recall this? The 8 and 2, one side is going to be 8, the other side is going to be 2. So we went through this FM and FP and add them, subtract them, and we know that this foot is not uplifting. It's not going up. So in this case here, we decided that the factor stress can be just multiplying the service stresses by a factor of 1.4. Where's the 1.4 coming from? Let's say it's going to be this one here. If someone have told me that this much is going to be the dead load, this much is going to be the live load, I would have tried the 1.4 dead versus 1.2 dead plus 1.6 live. But the problem was not clear. It just says the service load. So in a case like this, just going to be taking the 1.4 and use it. I ended up with a stress on the right side is going to be 11.2 and the left is going to be 2.8 KSF. So this is going to be the service stresses and this is going to be the ultimate stresses. Now I need to find out the reinforcement in this direction. What direction I'm going to see? This is going to be the longitudinal direction of the footing. The critical section I have, actually I have two sections. It's going to be one right here at this face and the other one also is going to be here. Now which one do you think is going to give me a higher moment? This section, when you look at the force coming from this side, is going to be one case. And the other case, look at the force in this side and look at the section to be in this side. So my question is going to be the right section or the left section? Which one do you think that I need to consider my analysis? The right. Why? Because the force here is going to be larger. You have here more pressure on this side than the pressure on that side. Does it mean that I need to do two sections and figure out the reinforcing on two sides? I'm going to say no. Whatever that you find out here, just keep it straight. If this section here and this reinforcing is going to be able to cover the moment in this case, so definitely is going to be able to resist the moment on the other side. Now the stress that you're looking here at is going to be trapezoidal in distribution. And it's going to be really tough to find out the centroid for it. It's going to be just taking maybe a couple of steps. So I decided here to split this stress into two sections. One of them is going to be this rectangular section, and the other one is going to be this triangular section. Now the question is, how did you find out the stress here? 7.7. I understand it's going to be 11.2, 2.8, 11.2, 2.8. By interpolation, if you can figure out the slope of this line, you can figure out that the stress here at this point is going to be 7.7. Now I'm going to have here two forces. One of them is going to be called F1 and the other one is going to be F2. F1 is going to be for this rectangular section, this rectangular distribution. And this force equals 7.7 which means the height of this rectangle times the distance x multiplied by the total width of the footing. Let me go back here one slide. I need to figure out this cantilever length, and then the width is going to be 10 feet. And here's the column size. It says here 16 by 24. So this distance from here to there is going to be 2 feet. 12 minus 2 is going to be 10 feet. You're going to have here 5 feet to the right, 5 feet to the left. All right. So here is the stress distribution. Here's my critical section, which is this dashed line. And here's the way to find out the stress at face of support, 7.7 by interpolation. And then you find out here two forces, F1 and F2. F1 is going to be equal to X, which is 5 feet. The width of the footing is going to be 10 feet. What do you mean by width? Means dimension in this direction is going to be equal to 10 feet. And with that, I have a total force of 385 for just this rectangular distribution of the stress. For this triangular distribution, I need to find out the height of this triangle. This height is 11.2 minus 7.7. So I'm working on this triangular distribution force, which means F2. I have 11.2 minus 7.7, which is right here. Look at this force here. 11.2 minus 7.7. Multiplied by 10 feet, the width, multiplied by the x distance, and then divide by 2 because I have, this is giving me the area, I have triangle distribution. So that's why I'm dividing here by 2. The centroid, or the point of application of this force, is going to be at x1. And how much is this x1? If I tell you here that this x is equal to 5 feet, how much is x1? I need help.
2.5.
2.5 feet. How about x2?
3.33.
Yeah, okay. x2 is going to be equal to 5 times 2/3, correct?
Yeah.
Very good. Why 2/3? Because usually this point load is going to be right at 1/3 from the base of this triangle. So the leftover of it, this x2 is going to be 2/3. This is why when you take the moment about this face is going to be equal to F1 times x1 plus F2 times x2, and this is exactly what we have in this equation. With that, I have 1254.17 kfoot. You have the depth of the footing. Now, can you figure out the reinforcing? I'm going to say yes. This is going to be so simple for me because I know how to play with this equation. It's just the S required. It's just an estimate for the reinforcing. I'm going to be assuming here 90% of the depth, right? And with that, I have 11.69 to be the needed cross-section area of the steel in the longitudinal direction. This gives me the reinforcing that I need to put right here, right at this section. So, okay, I'm gonna try here 15 number 8. I'm just trying here because 15 number 8 is gonna give me 11.58, 11.85. You can try any other numbers. It's gonna be up to you. You can use number 9s. You can use anything else. It's gonna be up to you. I mean, nothing's wrong with that. You can even try lower value. You don't really have to cover this. You can try maybe something's gonna get you here 11 square inches and see what Feynman you're gonna be getting. Having a quick spreadsheet to help you out in this is gonna be perfect because you can do it fast. Now the S provided is gonna be 11.85, slightly higher than this. It's gonna get you a tension of this much. Now compression block depth, you take ASFY, there is no compression, it is all rectangular section, and you end up with 1.74. And your Feynman, when you do the analysis, is 1254. How much was the demand? Excuse me, the demand is 1254. The capacity 1366. Meaning, if someone would like here to go maybe with 14 number 8, maybe it had worked. There wouldn't be a problem in this case. All right, again, you need to find out C over D and find out the phi factor. It is not shown here, but understand that you guys know how to do this, and there is no need to repeat the simplest step for you.
Professor.
Yes.
For the 0.9D for AS required, is that related to phi or it's its own thing?
No, this is an estimate for this value here, D minus over 2.
Okay.
Because in this equation here, if you have this phi meant to be the same as M sub U, you set them equal to each other, which means I know this value. Let me put a box around it. This is known. AS, I don't have it. I'm trying to have an estimate for this, right? Fy, yes, I can say is going to be equal to 6 KSI. The depth, yes, I know the depth. So in order for me to find out how much reinforcing I need, right, I need to have an estimate for A. I don't have it, right? I cannot figure out this estimate for A. So it is just easier if I take this value here, D minus over 2, and say this is roughly equals to 90% of the depth. So it is not related to the phi factor.
Okay. So if the phi changes, it's still 0.9D.
It is not related to it. This is not related to it at all. The question is, do we really need to assume that U is going to be 90% D? Can someone help me with this? Is it usually 9% of D? Can it be any other value? Can I use 0.85 D? Is it okay, or something's wrong with this?
I think you said
okay.
0.85 to 0.95.
Yeah, exactly, to 0.95. So it is not like a code. It is nothing that I have to follow. You can assume to be 95% and just come up with some reinforcing, and then you test it. How would you test it? You go through this exercise here to find out female. So this is not like code thing. This is just an estimate, and this estimate is based on practice. When you practice a lot, you're going to say, okay, let me just go with 95 or 90%, and this should be fine. All right, how about the other direction, transverse direction? So let me show you what does mean by transverse direction. I'm going back here, going back to slide 46. It's going to be longitudinal direction, and they have taken the section to be right here. It's giving the critical section for the moment. Now, how about the other direction? Now, my section needs to be in this case, like this. Now you have the stress distribution on this side, and then you should be able to find out the reinforcing in this direction based on this stress distribution and the force. So for the transverse reinforcement, it's going to be just repeating the steps. And I let you guys take care of this. This is just repeating this step here. But you need to understand the difference between the two sections. In one section, I'm going to be taking the critical section to be right here at face of support, and it's giving the stress distribution. In the other case, just taking the section to be right here, and then you need to find out the stress distribution below the footing here, which you have it already determined, but you need to find out the total force. Take it to the center of this rectangle, multiply by the distance, by the moment arm that you have the moment.
Professor, I had a question.
Yes.
On the stress at face support when we were doing the longitudinal direction.
Okay,
How
let
can
me
we-
get to it. Yeah, here.
Yeah, how can we use 7 feet instead of 5 feet?
Where's the 7 feet?
So right at F3U, so the stress at face support,
Yeah.
right below, it says 2.8 plus 7 feet times 11.2 over 2.8 or minus 2.8.
This one or this one? This one?
Up one more, that one.
Yeah.
So how can we use the 7 feet? How come we're multiplying by 7 feet, not 5 feet?
This one here?
Yeah. Correct.
Okay, can you try the number? Maybe just a typo. Maybe this 7 feet is just a typo. Good catch, thank you. Can you try the number? Is this 7 feet or 5 feet? Should be.
Let me double check.
Okay, good, thank you.
So if you do it by 7, it's 7.7. If you do it by 5, it's going to be 6.3.
Excellent.
Is there a column
So
width?
where is the 7 feet that I kept? I mean, this is excellent. Very good question. I like it. Where is the 7 feet measured from? Is it measured from here to there? Is this what they mean, maybe? How much is this? Do you know? It shows here total length of the footing to be 12 feet. Good. All right. So I know total length is how much? 12. If you put here 5, how much would you put here on this side? 7 feet?
Yeah.
The 7 feet is going to get you to where? To this face of the column. So it is correct when you use here 7 feet, right? If I use here this to be 5 feet, it means that you're trying to find out the stress right at this location, which I'm not interested in, right? I'm interested in the stress right here at this point. So this is the reason I've taken here 7 feet.
So then when you're saying the stress at the face, it's the furthest face then, correct?
It's going to be at
Because
this
since we're
section.
looking at the other
It
side.
depends on the section that you're interested in. So the section I'm interested in is going to be right this section here, right? This is going to be the critical section for the moment at this face.
Okay.
Yes.
Okay, perfect. Thank you.
All right. Thanks, Bill. All right. Now punch and shear. Question here is about the F1 and F2. Just a question came by. Just for curiosity here, is this F1 and F2, are they tension or compression? What nature of force is this? Okay, Jorge says gonna be compression. Compression on what? In the concrete footing, am I correct? Because they are pushing the concrete footing up. So if you like to call it this way, yes, I'm gonna say yes. F1 and F2 is gonna be compression because this is pushing here on the concrete to bend it up. If you like to see a good picture about this, I'm just gonna go back here, maybe slide 10, if I'm not mistaken. Okay, here we go. The stresses are pushing up this way, pushing the concrete footing. So they're pushing on it. So when you push against anything, it's gonna be compression. Yes, so it's gonna be compression. All right, now punch and check. Any other questions before I move forward to punch and shear? Okay. Punch and shear analysis. Punch and shear analysis, it happens in concrete slabs and also it happens in footings. So if you imagine that this is gonna be like extended concrete slab in both directions, and here's a column, which means this solid box, right? And then you have the concrete slab. Now the concern here, if the entire column here is gonna be just punching through the slab, if the slab is gonna be very thin. So this problem is gonna happen if the slab is very thin or the loading is so high. So you don't have good shear resistance, and this column is gonna be just punching through the column, the slab. This dashed line is gonna be the critical section for punching shear that we need to figure out how would we do it. If you have this given column here, you can call this to be the tributary area that the column is supporting. So you can take here the entire load, uniform load, multiply by this area, is gonna give you the column load. And then you wanna be sure that this column is not penetrating the slab. How would you do this? We're gonna be going through it right now. Here are some pictures of actual failure. As you see here, 65, and here's what happened. Part construction, look what happened for the column. Just the concrete slab just went down. There is no good shear resistance between the slab to column connection. So what happened? The column is just punching through the concrete slab. Look what happened here. You see, you remember this critical section for shear? Because usually the punching is not going to happen at the face of the column. It's going to happen at a bit distance away from it. Look at this. This is what we call here edge column, because it's going to be at the edge of the building. This is going to be interior column. And you see the problem? Just the slab fell down this way. Big disaster, right? Look what happened. Look at the slab column connection. Just a small piece is still within the column. And the entire slab just went down. Here's an actual picture for an actual building. And this was the type of cracks that was observed around the column. And by just looking at this, I said this is here punching problem. This slab is not strong enough, the critical section. This part here acts as a part of the column. Very similar to what happened here. Look, this piece here, it acts as to be a part of the column, not part of the slab. Same thing here. This is why this piece here stayed. Look at this. This here piece here is like a part of the column. And this piece also. Look at this piece here. So the same thing here. You look here at the after they remove the flooring, like the carpet or whatever that used to be there. Now look at the slab and look at this. It looks like kind of a circular shape, right? This is like on the perimeter of the column. That was about maybe 16-inch. So now we understand that we have here punching shear issue in this column. It needs to be fixed for this existing construction. This is a test that was done in the structures lab in the university. And look what happened. They put the slab column connection, and then they start to push force from the top with some hydraulic jacks, and this is the expected mode of failure. You see this piece here, it acts as integral part of the column. And look at the crack on the perimeter, it's gonna be like this. And of course, they take measurement here is about 10 inches to 11 inches, maybe 12 inches. And this explains here that from this point, which means at the bottom connection between the slab and between the column, if you go at 45 degrees, you're going to be giving yourself, this is going to be the critical section, which is going to be right here, right in the middle. Not here, it's going to be right here, like we're taking an average location. So to find out if this is going to be the column, to find out the critical section for shear, you're going to be going here d/2 distance away from the face of the column in both directions. Now, this is different from the one-way shear. In the one-way shear, we used to go d distance away from face of column. In here, we're doing it at d/2. So now, think about this section that you're going to be cutting, right? Which is this piece here, you're going to be cutting out of the concrete. Now, actually, what you're cutting through is going to be like this surface area of the concrete when the column intersects with the slab. This dimension, I'm going to call it here bx. Dimension for the shear section in the x direction, and this is going to be by. This bx is going to be equal to the column size in the x direction plus 1d. Why? Because you have a half in this side and a half in this side. So here's the equation. by is going to be also equal to c sub y column dimension, the y direction plus d. The perimeter, we're going to call it here b sub 0, is going to be 2 times this length plus this length, 2 times bx plus by. The sheared area during this punching shear process is going to be equal to b sub 0, the perimeter, multiplied by the depth. Depth is going to be from here to there, right? It's going to be the depth, like in here. I said, okay. Yeah, it makes sense. This is going to be the sheared area. The perimeter multiplied by the depth. It's going to be the surface area, right? The shear stress is going to be equal to the amount of force, V sub U, the amount of big force that you're talking about here, which is this force here. Let's say in this case, if we're talking here about the footing, it's going to be the column load divided by the surface area. With that, you're going to end up with some shear stresses that you need to resist. Now, this is going to be the demand, right? This is going to be V sub U. And in this case, you need to use the factor load, right? This is going to be V sub U, which is the same as P sub U for the column. Same as P sub U for the column. Design. It's going to be the same force that you use to design the footing or use to design the column. It's going to be this force is going to be causing the punching. So again, in foundation, we have here 3 checks. The first one is to find out the amount of reinforcement. Second one, you do one-way check, one-way shear. Second check is going to be punching shear. This is when it comes to concrete design. So we're working here in the third one. So this here, the demand, is going to be the shear demand, V sub U. Now, how about the shear strength? I'm going to say we're going to be using the same equation, which means PVC multiplied by the cross-section area. Now, instead of multiplying by the cross-section area here, we're just looking at the stress. So you don't really multiply by the cross-section area because you already divide by the cross-section area for the demand side, right? So now you compare stress to stress. So this V sub U here is going to be stress. So units for this stress is going to be in PSI. And units for this force is going to be pounds. Of course, it's going to be kips, and then you can multiply by 1,000 if you want to. Therefore, this VVC is going to be also shear. stress, which means it's gonna be also in PSI. And in one way shear, we used to say 2 square root of F prime C. In two-way shear, we don't say 2, we just call it the shear factor. And we'll find out how much is the shear factor. And the phi factor is gonna stay the same as the 0.75, like any type of shear case, right? How to find out the shear factor here? This is gonna be based on the column aspect ratio, which means column length by column width. It's gonna be based on the slab thickness relative to the perimeter of the column in critical section. So I have here few ways of doing it, few steps. The first one here, it says your shear factor is gonna be the minimum of the following values. Where's the first value? I'm gonna say here's the first value. You say it's gonna be shear factor sub 0, shear factor sub C, and then 4. So you have your 3 values, 1, 2, and 3. You take the smallest, the smaller of all the 3, the smallest value. It says here the shear factor sub 0 is going to be equal to 2 plus alpha s divided by beta sub 0. What is beta sub 0? Is going to be the perimeter divided by the depth. What is this alpha sub s? I have your 3 values. It says if you have interior column, it's going to be equal to 40. If you have an edge column, it's going to be 30. If you have a corner column, it's going to be equal to 20. So I said, okay, just some factors. How about this beta sub c? You see here for the shear factor for the column, 4 divided by beta sub c. What is beta sub c? Is going to be the column aspect ratio. You look at the long dimension of the column divided by the short dimension of the column. Many columns, they're going to have this beta of c equals to 1. So in this case, this factor is going to be equal to 6. And this factor, let's say, is going to be equal to 5. I'm just throwing a number there. And the maximum value is going to be equal to 4. Now you take the smallest of the 3 values here is going to be equal to 4. So the shear factor is not going to be equal to 2 like what we have in beams, but you need to figure it out based on this exercise. So I'm going to show you here an example at which we're going to see how this has been done. I've been taking here the same example that we started with when it comes to reinforcing. I'm going to have a footing here 8.6 by 8.6, 2 foot 6. The column is 24 inch by 24 inch. The concrete strength 3000 psi. The ultimate axial load 680. So this is already factored. This is going to be the demand. And this says, here are the answers. Footing is safe against punching shear. I said, okay, yeah, this could be one option, but there's some other options. Before I go through it, I'd like first to run the analysis on the punching shear. So I said, okay, let me find out here the critical section for shear. I have solved this problem before. I mean, in terms of the footing and the reinforcing, so I know the depth is going to be 26.5. I know that the column is going to be 24 inch by 24 inch. Here's the column width, plus 26.5 is going to be 50.5 inches for this length here, and this width here for the critical section 50.5 inch. Perimeter is going to be 50.5 times 4. It's going to be 202. The sheared area during punching process is going to be equal to this B sub 0, the perimeter, multiplied by the depth, 53 square inches. The stress, demand stress, is going to be equal to the 680 kips, which is the column load, divided by 53 square inches sheared area, to be, let's say, 127 psi. So I can say this now becomes 127 psi. Great. How much is the capacity now? That was the demand, right? The ultimate load, the demand. Now the capacity. Now let me look here at the capacity. This is here like interior column, because within the footing, this column is going to be right in the middle. If you remember, here's the footing, right? And here's the column. The column is going to be right in the middle. This column is not at the edge. What does it mean by the edge? Edge is going to happen. The edge case is going to happen if the column is like this and the footing is like this. This is going to be an edge case. A corner column is going to happen if the column is going to be like this. This here a corner column, interior column, edge column. So I said, okay, alpha S is going to be equal to 40. Now, another question here. Why did I take here 3.5 inch? Why didn't I take it 1.5 inch? Can someone help me with this? Just gonna stop here. This is gonna be slide is gonna be 62. I'm gonna go back to show you this example, so you know why I have taken it to be 3.5 inches. Anyone can help me with this? Why did I consider this to be 3 inches? Like what we said, the concrete cover for foundation is gonna be usually 3 inches. Now you have an estimate for the amount of rebar and the rebar size. So in here, I was trying to be conservative, so I assumed it to be an inch, as if the amount of reinforcement is gonna be big, real big. But now I know I'm gonna end up with number 8 rebars, or maybe number 7, which is about an inch. Half of it is gonna be half an inch. So I said, the clear cover is gonna be 3 inches, and to the center of the rebar is gonna be how much? Half an inch. So I said, total is gonna be 3.5 inch. And if I may go back here to my slide, it is gonna be half an inch. So 3.5 inch is what? Let me put it down here. Is gonna be 3 inch cover plus 0.5 of dB, the bar diameter, which is number 8 or number 7. All right, now I have alpha S of 40, interior column. This column is 24 inch by 24 inch. So the aspect ratio is gonna be equals to 1. And when you take here the perimeter divided by the depth, you can say which perimeter? You can say this perimeter here, 202 divided by the 26.5 is gonna be 7.62. Now I have 3 factors that I need to pick the lowest of all the 3. First factor is gonna be based on the column aspect ratio is gonna be equal to 6. 2 plus 4 divided by 1. The second one is gonna be 7.25. The third one, it says 4. The smallest of all the 3 is gonna be 4. So I said, okay, now let me find out this PVC is gonna be equal to the factor, which is 4, square root of 3,000 is gonna be equal to 219, and this is just VC. Multiplied by the phi factor, the 0.75, which is the same for all shear cases, now it becomes 164 psi. This is greater than the 127 that I end up with here as my shear demand. So this footing thickness is good enough. Any questions? Now in your project, you're gonna have a footing design. And in your footing design, you're gonna be doing 3 checks. Reinforcement, one-way shear, two-way shear. So first, you size the footing based on the allowable soil bearing pressure. Okay? Second, you need to find out the reinforcement. Third, you need to do one-way shear check. Do I have it here in the slide set? Yes, absolutely. It is right here. One-way shear check. We have it right here. This is gonna be the one. And finally, again, doing here the punching check. This is a complete footing design that you need to do it at least 2-3 times, because you're gonna see it in the midterm, and also you're gonna see it in your final. With that, I'm done for today. If you have any questions, please go ahead.
For the factor max there at 4, is that due to we're looking at a minimum of 4 inches for the cover, or what is the 4 for?
This is just a factor in the code. It has nothing to do with the concrete cover. It is given here from the code. If I may take you back here to this slide, right?
Mhm.
It is a shear factor, very similar to the equation to square root of F prime C. Now the equation is take the smallest of all of the 3 factors.
Okay,
So it's based on testing.
perfect.
Yeah. All right. If you have no questions, you can go ahead and sign out, please. And thank you for attending today's class.